Hi everyone, in this video we are going to review the Electron Transfer module. So the way I do my reviews is very fast usually, so hang on, but basically what I do is I split them into two different sections. I have a context section and I have a chemistry section. So my context section, which in this unit is a lot, there were a lot of facts here, so you just have to memorize. There's a lot of things you have to just commit to memory. There's no other way around it. Alternatively, we have our chemistry section. That is a lot of the application. Luckily for this module, it's not too thick, but the parts that we do have to do a lot of application for chemistry, it is a little challenging. So I highly encourage you to focus in on those little application pieces. So now at the end of this review, I have 3 questions that I think are the most challenging ones that you could possibly see on the exam for the application process. And so we're just going to go through those. I'll let you try them and then we'll work through them together. All right, so let's start at the very beginning. We're going to start with our context section. So again, this is the memorization, this is the facts, this is the information that I gave you throughout these videos. So the first thing we did is we started off by talking about just simple electron transfer, so not in combination with anything else. So in the very basics or the very simplistic manner, an electron transfer is just something that happens in a battery. All right, and so we talked about 3 different types of batteries. We talked about the NiCad battery, so you should know all about that. You should definitely know as much as you possibly can about the alkaline battery, which is the one we use commonly in our day-to-day life. You should also know about your lead-acid battery. Okay, so that's your car battery. And then the last thing we did in this little section is we talked about battery waste, or how to properly dispose of your batteries. And so that's something I highly care about, so you probably should know about that as well. After we talked about batteries, we moved into a fuel cell section. All right, so fuel cells are very similar. They use electron transfer, but they have a constant supply of fuel. And so in this section, we actually talked, and we kind of put a little tangent there, but we actually talked about using hydrogen as a source of fuel. Okay, so in that we also talked about using perhaps maybe methanol, C3OH, or ethanol as a different substance, and we actually talked about how we could clean that process and able to actually extract the hydrogen out of these starting materials of your methanol and your ethanol, and then use your hydrogen as your fuel source. But we did spend a lot of time on that, and we did look at the schematics, so I would definitely make sure I know that. We also talked about the possibility of splitting water. So what we did there is we talked about taking H2O and splitting it into either your oxygen gas or your hydrogen gas. So we talked about it conceptually and how it requires a lot of energy. So 249 kilojoules of energy per mole is needed in order to actually split water. And so it's a very difficult process, even though a lot of people really want to spend time and money on that. Then for fuel cells specifically, we really focused on in the PEM, or the proton exchange membrane fuel cell. Okay, so I would make sure I understand that schematic very well and know exactly how you go from your anode to your cathode and exactly where they are located on that fuel cell. After we talked about fuel cells, we moved on to a different type of cell, or a PV cell, or a photovoltaic cell. So now a photovoltaic cell is just when you take light energy that comes in, so your incident radiation from your sun, and you convert that to electrical energy. So for a PV cell, we focus on 3 main things. The first thing we did is we talked about the construction of it. We know how we can take a cell, and then we can convert it into a module, and then we put several modules together, and we actually are able to create an array. The array is what you see out in public. So you see a lot of photovoltaic cells smashed into one little section. We also talked about how we can use photovoltaic cells. We can use them just in a panel, so a single panel like we saw with those gentlemen that were able to pump their water by using a solar panel, but we also saw what's called a solar park. And so we know what a solar park looks like. We know the direction of the solar panels, that in the northern hemisphere, our solar panels have to face the south. If in the southern hemisphere, our solar panels have to face the north. If they don't, we're not optimizing our incident radiation. It's just a waste of everyone's time and money. And then we also talked about optimizing PV cells. How do we get the most efficiency, or how do we get the best efficiency or the most electrical energy from this system? And what we learned is that if we use multiple PN junctions, so that's your P-type and your S-type, or your N-type semiconductors, multiple ones of those, especially 36 of those, we're able to increase our efficiency to 72%, which is ludicrous. That's absolutely awesome and such a huge number. So that's very important. All right, so that was just simply electron transfer by itself. Then what we did is we did some kind of combo sections, and I'm just going to call it combo. So what I mean by that is electron transfer, And then I'm just going to say plus X, okay? And this X is going to be variable. But we looked at a couple different systems that use electron transfer with some other source of energy, some kind of battery or something like that. And so the first thing we looked at were our hybrid cars. So our hybrid electric vehicles. So our hybrid electric vehicles, which we refer to as HEV, were just something that we use a gasoline engine, but they also had an electric motor. And we talked all about the combination, how they work together, and when one works, when the engine works, when the motor works. We talked about all that. From there, we actually took it one step further and talked about the plug-in hybrid electric vehicles and the different aspects of that. So I'd make sure I know the difference between the two. Then we also talked about electro chemical cells. We actually looked at a schematic of that, and so I would be very comfortable with that schematic. I'd make sure I know where the energy comes from, where it starts with, so it comes from the sun, and now how we're able to convert our chemical energy into electrical energy. So the photoelectrochemical cell is actually one of the most beautiful pieces of technology that we talked about in this module. After that, the last thing, and I'm just going to put this very, very briefly, I mentioned shortly how we can actually use algae using its photosynthesis process to create hydrogen gas, which we can then use in a fuel cell. So this was definitely one of those combo pieces. We didn't spend a lot of time on it, but be familiar with it because algae could be the future. That could be where we go, which would be really, really neat. All right, after we talked about our combo pieces, we then focused on four main sources of renewable energy, or renewable energy sources. And so we did a couple bullets for each one of these. So I would just make sure you're very comfortable with solar thermal. So that's when we take a bunch of mirrors and we point them in one direction. And so we basically focus the solar energy into one specific spot and to try to heat up water. We also talked about wind energy, how we heat up the kinetic energy, heat up the gaseous molecules, and then we provide them with kinetic energy. That goes to the turbine, which then goes to the generator. So we talked about wind. We definitely talked about water. We've talked about that before as well. And then lastly, we discussed geothermal and how we are able to actually use the energy that's down deep into our Earth's core, specifically in our water reservoirs, and how we're able to kind of funnel that hot energy or that steam energy, that high kinetic energy, again, put that towards the turbine so we can convert to mechanical energy. Then from there, we put it in a generator so we can convert to electrical energy. But the big overarching theme here in the context section was efficiency. We kept talking about efficiency for each plant, each section, everything that we talked about, we always mentioned efficiency. And so make sure in the back of your mind that you are comparing everything that we talked about in this module to the efficiencies that we learned of from coal and from your nuclear power plants. So we're comparing all of these together. So combustion, nuclear, or in this case, electron transfer. Okay, so if you remember, this is going to be our last unit where we're actually talking about energy and how we can use energy to warm our planet. The next two modules are going to be on something entirely different. So this is the end. This is the last piece. This is where we end this story. Okay, so make sure you get all of this right here. Now, from here, we moved into the fun section, the chemistry section, the fun, exciting, wonderful part that probably gave you a headache or two. Apologize for that, but it is what it is. So now the chemistry section, the big topic is we discuss the difference between heat and work. So we know that electron transfer is all about work energy, okay? Organized molecular motion. Coal or combustion is definitely when we're looking at heat or heat energy. So it's chaotic, it's unorganized, and so we're comparing the two. But remember that this whole unit, electron transfer, we're focusing on work energy, all right? So then what we did is we looked at the difference between oxidation and reduction. Okay, so we kept it quite simple this time around, and so we just needed to identify what oxidation and reduction reactions are. So the first thing that I expect you to be able to do is to identify them. Are you looking at an oxidation reaction or a reduction reaction? After that, I 100% expect you to be able to balance your half reactions. So you need to make sure that you can add enough electrons to one section or maybe take some away, but you need to make sure that you're adding those electrons in and then balancing them properly. The last step is that coming up with a total chemical equation. Okay, so that's when you finally combined your two half reactions. Remember, your half reactions always come in pairs. You have to have an oxidation half reaction and you have to have a reduction half reaction. When you add the two of them together, your electrons will always, always, always cancel out. If you ever have electrons in your total chemical equation, you know you've made a mistake. So go back through and recalculate. All right, so then after that, we use this information of oxidation and reduction to explain what electrochemical cells are. Now we focus on two different types of electrochemical cells. So let me split these up here for you. The first one we looked at were our galvanic cells. And then the second one we looked at were electrolytic cells. Electrolytic cells. So your galvanic cells were your spontaneous processes, okay? The ones that occur by themselves in isolation. Your electrolytic cells are your non-spontaneous processes. These will not occur by themselves. You must have a battery or some kind of energy source. You need to supply energy. Because remember, galvanic, you're going from high energy source to low energy source. It spontaneously happens. This electron transfer wants to occur. Electrolytic is the opposite. You're going from low energy to high energy. There's no driving force. There's no reason for those electrons to jump ship and go from the low one to the high one. That's not going to happen unless you have an external energy source that can add energy to this electron and it can whoop, jump right up to the top space. That's the only way that process is going to happen. All right, so those are our two types of electrochemical cells. Once we were within the electrochemical cells, all this information is always the same, regardless of galvanic or electrolytic. So first things first, your anode is the electrode at which oxidation occurs every time. It doesn't matter if galvanic, doesn't matter electrolytic. Oxidation, anode, always, okay? Your cathode will always be the site at which reduction occurs. Always, always, always. So remember, vowels go together or red cat, but there's just a way to remember that. Now, the second thing, or the third thing I guess I should say, is we talked about what a salt bridge is. Now we know, based on the different examples and all the different batteries that we looked at, sometimes your salt bridge is actually an electrolyte paste, and that's completely fine, but all it does is it allows for the charge or the transfer of charge or the flow of charge. But we need to have some kind of salt bridge or some kind of paste in order to make sure that everything is balanced, because otherwise you have a buildup of charge, all right? After that, the last thing we talked about and we stressed is that regardless of your system, electrons are always going to flow from your anode to your cathode. Always, always, always. From anode to cathode. You have oxidation, electrons go from anode to your cathode where you have your reduction. Every single time. Have I said that enough? All right, now, after we talked about electrochemical cells, we went and looked at the chemical aspect of using hydrogen as a source of fuel. And so the big piece that I want to point out here is that we understood that there's a lot of potential energy stored within the bonds of that hydrogen bond specifically, right? So we learned that if we actually combust hydrogen or use that potential energy or the chemical energy that's sitting inside that hydrogen bond, we actually can release 124.5 kilojoules of energy per gram burned. Keep this in the back of your mind. We compared that to wood, which is 10 to 14, coal, which is 30, petroleum, 48, natural gas, 50. Hydrogen is 124 kilojoules of energy per gram. This is our best option if we can possibly find a way to create enough hydrogen and use it safely as a source of fuel. Now, the next thing we talked about was splitting water magically, right? It was not easy. We talked about the process of going from water to hydrogen plus 1/2 O2. Specifically, I'm putting this in the chemistry section, even though I know we already talked about it, because I want you to remember what electrolysis is. That is a very, very common word. We hear it all the time in just global conversations, not necessarily from scientist to scientist. So please make sure you're familiar with what electrolysis is, because that is definitely something you will hear in the future. The last thing that we did for the chemistry standpoint is we focused on what semiconductors are. And in this course, we really just focus on silicon, okay? So we focus on silicon, and we know that there's two different types of semiconductors that we can create when you dope them or when you add some other element. So not silicon, any other element but silicon when you add that to the semiconductor. So the two we looked at was an N-type, so your negative semiconductor, and that's when you have an extra electron. So you've added something, an element that has one more electron than silicon naturally has. I'm talking valence electrons, remember. And then the last thing that we looked at was the P-type semiconductor. And so that is when you have a positive type. So you're missing an electron. And so this is usually an element that has one less electron than your original state did, which was silicon in this case. All right? So that's everything that we talked about in this module. It's a lot, but make sure you get it down. There's so many facts. The only way you're going to do well on this exam is if you drill, and you memorize as much as you possibly can. I would highly encourage you to get a study group for this one, because there's so much information that you might miss it studying by yourself, but your buddy might pick it up, and then by having that conversation, you will be able to cement that into your brain. All right, so now we're going to our three hardest type of problems that we could possibly see on the exam. Like I said, there's a lot of memorization, so there's going to be a lot of facts that you need to have. But in terms of the application process, it primarily has to do with the doping or your half reaction. So let's practice both of those. Question 1. If I give you magnesium solid, we treat it with tin 2 plus in the aqueous state, and it goes to magnesium 2 plus also in the aqueous state, and tin solid. My question is, can you please write out what the oxidation half reaction is? Okay, draw it out. Go. All right, did you get an answer? Hopefully you did, but if you didn't, that's okay. The first thing you have to do is draw in your little zeros here above your magnesium and above your tin. We know that any element by itself, it definitely has an oxidation number of 0. So now we're looking for an oxidation half reaction. So we're looking for something that lost electrons or became more positive. So what I see automatically is magnesium went from 0 to +2. So it became more positive. That's a huge red flag that we are looking at an oxidation reaction. So what I would do personally is rewrite it down here, magnesium solid going to magnesium 2 plus. And then I just try to add my electrons to see if I'm right, and then I actually have to add my electrons to my product side or my right side to make an oxidation reaction. And I do. If I balance this properly, I see that 2 plus 2 electrons is definitely going to get me to a neutral magnesium. So the oxidation half reaction here is just magnesium going to magnesium 2 plus. If you want additional practice, I would highly encourage you to try to write the reduction half reaction now. Number 2, if I give you zinc solid and I tell you it goes to zinc 2 plus in the aqueous state, and then I also give you iron 3 plus in the aqueous state, and that's going to iron solid. This is all the information I'm going to give you. I'm going to ask you to solve for the total chemical equation. Do not forget to balance. Go. All right, did you get an answer? Hopefully you did, but if you didn't, that's okay. This is definitely one of the most challenging questions I could ask you in terms of putting your half reactions together. So the first thing you do is you need to identify, is this oxidation or reduction? So let's start off by looking at zinc. So what I see is that my zinc goes from zinc 0 to zinc 2 plus, so it becomes more positive. That is a classic sign of an oxidation reaction. So what I can see is that there's a difference of 2 electrons. So I'm going to have to add 2 electrons to my right side. This is definitely an oxidation reaction. So what that means, instinctively, you should automatically be looking to see if you can add electrons to the left side of your iron 3 plus. If your first one's oxidation, your second one has to be reduction, or else you've done something wrong. So use that as a way to go back and check. So what I see first is my iron 0 is on my product side or my right side, and then I see my iron 3 plus is on my reactant side. So I see that it goes from positive to neutral. So it gains an electrons. Classic sign of a reduction reaction. Now we can see that it goes from 3 to 0, so we definitely have a difference of 3 electrons. This is definitely a reduction reaction. Now, the biggest thing, always check your electrons. What I see is 2 electrons for my zinc, 3 electrons for my iron. These are not balanced. The only way you can properly balance this is by multiplying each one by a coefficient. So just like we have done before with chemical reactions and chemical equations, we need to do this similar here. So now, the only way to get each of these to have the exact same number of electrons is to get both of them to be at 6 electrons. So I'm going to multiply my zinc reaction, my equation or half reaction, by 3, and I'm going to multiply my iron half reaction by 2. So let me come down here and rewrite this. So I have 3 zinc solid going to 3 zinc 2 plus aqueous plus 6 electrons. Okay, that's my oxidation reaction. Now my bottom one, my iron, that now becomes 6 electrons plus 2 iron 3 plus in the aqueous state, the phases never change, going to 2 iron solid. All right, so now I have added my electrons, I've balanced each component, so now what I want to do is make sure that everything cancels out, specifically my electrons. So I see 6 electrons on my reactant side, 6 electrons on my product side, they cancel each other out. Now I look, zinc 0, zinc 2 plus, not the same thing. Iron 3 plus, iron 0, not the same thing. So what we do is we bring everything down here. We have 3 zinc solid plus 2 iron 3 plus aqueous goes to 3 zinc 2 plus aqueous plus 2 iron solid. Beautiful. This is your final answer. That is the correct answer. So hopefully you got that. If you did not, please don't get frustrated. All that means is you need to practice. Just more practice and it will click, but you just have to keep doing it over and over and over again. One thing I want to point out is that the order of this does not matter. So if you had written 2 iron 3 plus 3 zinc, that's completely fine. As long as your piece is correct, so your coefficient and your ion are correct, that's fine. But the order in which you write it is not important. All right, last thing, we're going to number 3, okay? And so for this one, we are on a new planet, okay? That's the first thing you need to understand. We are on a new planet, make up some name, whatever, planet Bieberdorf, whatever you want to call it, new planet. So now, on this planet, instead of using silicon as our semiconductor, we're going to use phosphorus. Phosphorus is our semiconductor, okay? So think of it in terms of silicon. Think of how we did this before. So now what we're going to do is add 3 different components to it, okay? So the first thing I'm going to do is add tin. The second thing I'm going to do is add nitrogen. And the third thing I'm going to do is add selenium. So now we have 3 different samples, okay? 3 different beakers. We're keeping everything separate. This is not all at the same time. So I want to know, when I dope my P semiconductor with tin, what happens? Is it an N-type or is it P-type? When I dope my P semiconductor with N, is it P or N? When I dope my P semiconductor with selenium, Se, is it P or an N-type semiconductor? So you have 3 different questions, okay? Go. All right, did you get an answer? Hopefully you did, but if you didn't, that's completely fine. The only way you can solve this problem is you have to look at a periodic table. So the first thing you should do is look at phosphorus and go, okay, I know that this is a group 5 element, so it has 5 valence electrons. You're going to compare that number to all these other ones for selenium, nitrogen, and tin. So let's start off by looking at tin. Tin exists in group 4. So if we add something with 1 less valence electron to P, to phosphorus, the only type of semiconductor we're going to create is called a P-type semiconductor, okay? Because we're missing an electron. We've added a hole, all right? So now let's look at selenium. Selenium is a group 6, okay? So it has 6 valence electrons. So if I add selenium to phosphorus, I'm adding an element that has 1 more electron than phosphorus does. So this definitely has to be an N-type semiconductor. It's negative. There's an extra electron. Now let's look at nitrogen. Nitrogen is also in group 5. So if I add nitrogen to phosphorus, this is a nothing. They have the exact same number of valence electrons. So doing that would not be advantageous. There's no reason why you would ever add nitrogen to phosphorus unless you're some weird scientist and you just want to do it for fun. But there's no reason. If they're in the same group, you don't want to do it. Hopefully that makes sense. Good luck on the exam. Study. Make sure you're sleeping. Make sure you're eating green stuff. You've got to get your broccoli in there. And make sure you drink water. Have a great week, guys.